Hello, hello, hello. Okay. Hello, everyone. Good evening. Are we live streaming? Okay. This is working now. I think it's out of battery already. You just got to angle it. Really? Like that? Yeah. Hello, everyone. I'm very excited and so happy that this is happening. It was quite some time in the making, talking to Tony Ruto from Autodesk. This is something that is relevant for all of us, and it will unfold slowly. The title is Physics-Informed AI, Gravity and Creativity. Gravity is one of the banal forces, but very, very powerful. And you will see immediately how each of the speakers will relate to it in some way. The format is quite friendly, fast, and it's about hopefully engaging you in a conversation. So we'll have 6 speakers, 10 minutes each, so quite quickly, quite fast. Andy Lomas will finish the session with a little bit more time because he will share something really beautiful with us, which is a small animation that he prepared for Max Cooper. So just a little bit about the running order. Tony Ruto, Senior Director, Autodesk Research. I know Tony for many years. Andy Harris from Tony's team, Director of Manufacturing at Autodesk. Nathan Kutz, sorry. Slightly different. I know the Katz, but Director of Physics-Informed AI at Autodesk. A new, not new territory, but kind of a new position. So really interesting. Anat, senior associate at Zaha, did a very dear friend for many years. Wonderful work. I will show some of the design context, so more, the object, going down into the object world, really, and manufacturing. Just want to say thank you for PCAD and for David Frame, that is not here at the moment, maybe watching us somewhere, but did such a great job to produce everything, and the LTS team. A big thank you to Autodesk Research. This is the 2nd year of sponsoring or supporting the course with 2 scholarships and 1 award this year. Thank you very much, Tony. I really appreciate your personal engagement, making it kind of happen, and with your team. So thank you very much. That's really, really greatly appreciated. Some of the scholars are here in the building. Can you raise your hand? 1, 2, 3. We also have this year highly commended, that is not here, I think. Honi? Is Honi here? No. No? Okay. Hopefully you will meet Honi later. So thank you again. That means a lot. It's a life-changing thing for the recipients. That's the last slide for me. Before we start, I just want to position, some of my students know the slide already, so apologize. Just to show everyone where we are right now in history. We are after 4 industrial revolutions. Industry 5 is not an incremental revolution at the moment. It might turn to be one, but what's interesting is that we are moving from, hands power, like fingers and hands and bending and shaping, to, steam engine, beginning of machines, really. Computation is actually not new anymore. But where we are now, of course, automation, digitalization, Industry 4, but where we are now in a really wonderful point in history where some say we're moving from the information age to the imagination age. It means that math and physics is of course very important, of course very important, but our world of design, process design thinking becoming more and more powerful, I would say. So imagination, using experience-led learnings becomes very, very interesting, and we'll talk about it as part of the symposium. So I will put a pause now and switch to Tony. How do we do that? That's laptop, yeah? Okay, cool. Stop share. This is when we need technology. Always the same story.
There it is.
Yeah. Cool.
So thank you, Assa. Oh, it was back and went again.
Yeah. Oh.
Okay.
Back. Yeah.
Don't touch anything. Safe harbor statement, folks. Ever so brief, but brief, in quotes. This is a statement we tend to put out when we share potentially, leading research in terms of what we're doing at Autodesk, and it's just to say what it says. We always show this for roughly 30 seconds to a minute. And then what we can then get into is like really share some leading research and what we're doing at Autodesk. So please take a moment to read it. I shouldn't summarize on your behalf, but a few seconds will do. Okay. Hi, Tony Ruto. I lead research engineering in Autodesk, and specifically in the research team. So my team's role is to partner with industry futures teams that Andy leads, for example, and also science teams, and Nathan will be leading an aspect of the science teams that we have in Autodesk Research. And the goal here is to help the company innovate for the future. So my team will be helping engineer innovation. We focus on what might come next. We think about new paradigms for design. If you think of generative design, which we'll touch today, we would have played a key hand in developing that technology and advancing it to where it is at the moment. We are also investigating generative AI. It keeps flickering.
Why or something?
Oh, do you want to use? Yeah. Right, second time lucky, perhaps. Right, so in this talk, ever so briefly, I'm going to focus on AI-enabled tools for design and make, just cover the history of Autodesk and what we've been doing with AI, and really showcase some of the new solutions we have on offer. And I'll then hand over to Andy, who will talk about the industrial application of these tools. And then Nathan will bring us home with a physics-informed AI perspective. How can we improve generative AI by bringing physics into the mix with that technology? So Autodesk has a long history of developing AI. So while AI might seem like a new technology in the architecture, engineering, construction industry, what we have been doing, for example, in multiple areas, has been really around exploring what AI can do in product design, in building design, and other domains, including in media and entertainment. So we've got over 15 years of investigation and publishing papers as well. In 2009, the first publication on generative design was released. And this was very much the beginning of a lot of the work and focus. And then in 2018, we created an AI lab, and that was the beginning of accelerating a lot of our AI investigations, specifically again for design and make. In 2019, the first generative design capability was released, and this was Construction IQ, really to assist with risk analysis and safety via the BIM 360 application. We've since released other generative design solutions, both in Revit and in Fusion since then. In 2022, we published a public dataset. This is the Fusion Gallery dataset in partnership with MIT. Again, this is work that came out of the AI lab. And then if we fast forward to 2024, the first 3D shape generative AI model was released, at least as a project, a research project called Project Benini. And this was a publication that was then formalized as an actual working solution and demonstrated in some of our external engagements. Now, we're obviously in 2026. A lot has changed in just the last couple of years. So let's look at the generative technologies, which are AI-enabled technologies out of Autodesk today, right? So generative design and generative AI are two distinctly different technologies, right? And so the key things to consider here are, generative design is really focusing on evolutionary algorithm approaches, and it's very much looking to optimize geometry based on a number of factors. I'll kind of go into a bit of detail around this on the next slide. And with this very same input with generative design, you will get the same output. It's very deterministic in nature. That's the way it's set up to work. It's using simulation as the basis to evaluate geometries that are proposed or generated, and then it's revising those using an algorithm to ensure it can achieve the performance target of the user's goal. Now, with generative AI, it's very much machine learning based, and therefore it is not strictly deterministic. For a given input, you can receive multiple outputs, which are highly likely, using that term likelihood for probability, because based on your input, this is likely going to be the solution it can generate. And that's what generative AI does. It proposes solutions. It's extremely fast, but it's a very different type of technology compared to generative design. Now, let's take a bit of a deeper dive into generative design and consider what physics might look like in practice. Right, so what you see here is the setup for a suspension part for a performance car. And there'll be a number of different boundary conditions being used to define the physics of this particular geometry, right? Specifically, when I say physics here, I mean, what is this part going to do in the specific function that it operates in, right? So in this particular load case being illustrated, that suspension arm connects to the upright of a wheel, and the arrow you see at the bottom there is where the tire position on the ground is where force enacts. And this force then is obviously connected to the wheel, which connects to the upright, connects to the suspension arm, and all these rigid boundary elements are being used to provide that notion of connectivity. Other boundary conditions that are used here and defined are going to be constraints, some of the kind of locked points you see on screen, and there'll be other things like contacts, which are also considered. All of these things define the behavior expected of this part when it's in operation, and you can have multiple load cases. From these, we can then use a generative design algorithm to achieve multiple options for geometry. Now, not just one, but multiple, but each one of those will actually address the specific performance requirement of the setup. Now, I did say it's deterministic. What we're exploring here is if we were to change the material type or manufacturing method, then we would get different options, but each one of those, again, still meets the criteria. So if you were to lock it down even further and say, only give me for this one specific manufacturing solution and material, then you probably only get one output, right? But if we're going to vary some of the input elements, we will get some variation in what's then generated as multiple solutions. Simulation is very important, as I mentioned. So for every iteration of generative design, it is using simulation to verify whether the current geometry can meet the performance target of the user's intent. And in this case, we're showing Autodesk Nastran being used to see how this part will buckle under load, and is this within the safety factor of that particular part? So these are things that are considered. And then finally, we have to manufacture the part, right? So in this case, this generated output focused on CNC milling as its particular manufacturing method. The generative design algorithm will also offer an approach where it can tune every geometry to meet the target of the manufacturing process. An additive solution will likely not look like this. Now, one thing I'll just also say as another sort of control mechanism for generative is the notion of preserved elements or preserved shapes. So if you consider the blue section of this geometry shown here, that's the design volume that is being optimized. Everything else that's not blue is a contact point, right? And there's also going to be shapes within that blue zone which are access points. So if you can imagine, like there likely will be an axle going through this part or some kind of rod that needs to have a space to go through. So that area of the geometry is also preserved. And the final output that comes out from generative will keep all of these things intact while also optimizing the rest of the volume to achieve the goal. So as I said, it's a very controlled, very deterministic approach. It does consider physics. It therefore leads to a high performance part in geometry at the end of it. But let's consider what generative AI can offer as an advantage, right? So here we are looking at how generative AI can provide a mechanism through which more accurate shapes can be created as part of the design process. If you consider that your first step in 3D design is to sketch, you do your 2D sketch and then you extrude to make your 3D. What we're showing here is how a generative AI model that was trained on constraint data can actually automatically generate constraints for your 2D sketch and propose those as alternatives for the user. So the goal is, as you continue to design further, what you're going to see is the ability to maintain the exact dimensions, but even as you scale up, the same dimensions or ratios between the edge lengths and so on will be maintained throughout the process. So this leads to a mechanism where you can actually preserve accuracy of your base sketch and create 3D shapes that are quite consistent with what your intention is. In this case, generative AI is assisting with preserving accuracy and, in fact, improving it in many cases. So you can get your work done better and faster, certainly, because it takes a fraction of time to generate constraints versus you doing them by hand. So consider that performance is a key contributing factor here for generative AI. If we then look at the notion of CAD precision, right? So here we're going to see a neural CAD for geometry model generating 3D shapes that are CAD. They are not point clouds. They are not meshes, they are not voxels, these are CAD geometries. And we announced this model in the Autodesk University event in 2025. But you can see here that the speed of being able to go from a simple prompt to a 3D geometry is quite fast. This is running live. Recorded live, I'd say. It's not running on the laptop. But it's recorded live, and you can see how fast it takes to generate these particular shapes. It is much faster than doing this by hand. Each one of these geometries is CAD. It can be edited in Fusion or your preferred CAD tool. And it's important to state that CAD gives you precision. A mesh output will not be as precise as this. Neither will a point cloud be. So in this case, generative AI is assisting us with achieving precise CAD outputs. Now, combining generative design with generative AI leads to a very interesting unifying factor here, which is you can very quickly end up with initial geometry with generative AI and then achieve performance geometry by plugging in generative design. So both technologies are very powerful when combined. Now, when we consider how physics might fit into this, as I showed, physics fits into generative design, which is the slow process, but imagine if we could bring that into generative AI and achieve the speed and performance gains, but also doing so with physics being considered as well. And that's something that we can consider for the future. So I'd like to just conclude by just describing the changes that have happened with CAD tools over the years, because I think, as to Assa's point around, we're in a very interesting time. There's the same thing to be said about design software. So initially, parametric 3D design was it, right? You could set up parameters and really sort of create very advanced or very complex geometry. But you had to define parametric rules and how, as I shared in the auto-constraint method, you're defining what these edge lengths are, the equivalent ratios, and you would build all these rules up to create something that's fairly complex geometry. We then moved on to computational 3D design, which is where you're providing programmatic rules as to how to create geometry. Now, this is kind of like, we're going from like maybe 20, 30 years ago to maybe 10, 20 years ago, right, in terms of the technology, right? And still, we can now create very sophisticated large models, but as designers, you need to learn how to program these particular types of rules and so on. So the designer is still programming in this case. I've just shared some context around generative 3D design. Now, the illustration here looks at generative design applied to architecture, engineering, construction, or AEC. So this is in concept planning and development for building designs. But in the same case, you're still having to provide some fairly complex inputs. As a structural engineer, as I just shared, what are the loads acting on this part? What boundary conditions am I going to define? What criteria needs to be met, like in terms of like safety factors and natural frequency constraints and so on? You need to really understand deeply how to use these tools, which unfortunately leads to a situation where not many designers have taken this on as a thing because it's very complex. It only appeals to specific advanced engineers who can really leverage this tool to the max. But herein lies the opportunity, right? As AI powers 3D design, we're now in a situation where you can leverage AI, right, to analyze what you're doing, to automate some of the processes like the auto-constraint step, and also to augment your capacity, right? Consider that you're now able to work much faster as you combine these tools together. Consider that with generative AI combined with generative design, you're getting performance productivity gains, as well as performance geometry out of the system. So together, you're very much able to work a lot faster and improve what you're doing. And importantly, with generative AI, it's a very interactive but very natural approach to being able to do design. So anyway, that's the path we're all taking. Software continues to evolve, but this is where we're at today. I'm going to sort of conclude and say thank you. I'm going to hand over to Andy. So Andy's obviously got some... Thanks very much. So Andy is part of the Industry Futures team, and they look at industrial application of a lot of the technology my team will develop. So Andy will share that.
Thank you, Tony. Yes. So yeah, my team focus on the application of these technologies. So Tony's shown some of the kind of ground-up work that we do on some of our software tools, but actually we need to apply these to real customer problems. And that's where we actually learn a lot, because there's a lot of kind of real data, real information that's involved in this. I had a lot of projects I could have shared with you, and I really wanted to share this one. It's the one that excites me the most. It basically looks at the design, simulation, and testing, and then learning from that in order to improve our tools. So I'm actually going to show some prototype tools, but by the end of this project, they're actually in the product. So it's pretty cool. Okay, so we worked with a number of universities on this project. It's part of the Clean Sky 2 initiative funded by Horizon 2020. So yeah, we worked with University of Hamburg, University of Dresden, and also General Electric. So the part that we're working on, it's a turbine center frame. It's part of a jet engine. There's over 100 components in this, and we wanted to optimize it. We wanted to improve it to reduce its mass, make it more additively manufacturable. And the reason why we want to make it additively manufacturable, because this part's made out of Inconel. Inconel's really hard to machine, and the material gets harder when you're trying to machine it. So you ruin loads of bits, you waste loads of material. Aerospace care about something called buy to fly. They care about something where you don't waste too much material when you're making components. So actually, if you get near net shape using additive manufacturing, you save a lot of money. So this is where the turbine center frame is located. It's located towards the rear of the engine. It holds the high speed and low speed spools together. It has a very high precision bearing in the center. And around the outside, some of the components that are not shown, but you can see those struts in the middle. There's some ducts that sit around the outside. Those feed air into the center and oil to lubricate and cool the center bearing. So you can see here where the component is located towards that rear section of the engine. This is the stages we went through. So we got loads of requirements, models from General Electric. We wanted to look at how can we apply multi-physics generative design to this. So we're not just doing structural analysis, we're doing thermomechanical, we're doing CFD analysis, and we're trying to combine it all together into one system. So we had to go and build this component, test it. We worked with the universities to do that. We did some proper aerospace level testing as well, because these guys can test parts for jet engines. And then we go and build it. We built this whole thing. You'll see it at the end. So we went through a number of design iterations. We had to evolve the design slowly, build it, design it, simulate it, build pieces of it, and then test it learn from that, and then improve the design iteratively. And as we went through each stage, we met more and more of the requirements until we got to the end, where we met all the requirements. So the first stage was to look at some generative design. We wanted to understand a little bit more about the structural performance of this. Can we add, where do we need to add material? Where can we take away material? And this is where generative design suggested we could add some material to this component. So you can see the structure there where it's added some material towards the bottom. Actually, later on, I'll show you that we actually made this a bit of a sandwich panel, so that top section of extra material just got absorbed by that sandwich panel, so it wasn't needed. We added a lattice. This is a really complicated lattice. It's a double conformal lattice. It conforms around the shape and at the angle of the shape. And the lattice is also optimized. It's varying thickness. So this enabled us to get a mass reduction of 35% compared to the original component. It met all the stiffness requirements. This is the over 100 components merged into one that you can see here. When you do that, you merge a lot of functionality of components together as well, which is why we had to take this multi-physics approach. There's a close-up of the lattice structure. You can see right in the middle there is optimized. It's varying thickness. So yeah, we had to do some extra analysis on this, as well as the structural analysis to work out the displacements. There's a fatigue requirement as well, so it's thermomechanical fatigue testing we had to do for this. It's basically as it heats and cools during its flight cycle, you grow cracks slowly. So you want to make sure you don't grow them too large before the end of the life of the engine, or the expected end of life. So yeah, it's a cyclic load that increases and adds tension to the material. Okay, so this is the next kind of physics, CFD. We had to do some generative fluids. This was actually the most prototype tool that we had that is now in the product, but you could do fluid optimization. So we had to do a lot of testing for this because originally it was designed for mold tools, for liquids. We wanted to adapt this to now work with air. So we had to do a lot of learning, gather a lot of data to improve that solver. You'll notice that section is actually attached to the body. In the original part from GE, it's not. It's just floating. It's a parasitic weight. It adds nothing to the structural performance. So we've combined it on there to make it easier for the additive manufacturing and also add to the structural performance of the component. We got a pressure drop reduction of 91% because we've got a nice free-flowing shape. Very few eddies and turbulence within that volume that you can see there. Yep. And then the last bit was this sandwich panel that we added. It's really good for additive manufacturing, especially with, it's a powder bed laser process, so you get a lot of heat in there. If you use thinner structures and lattice bodies, you reduce your distortion. But it also, in this case, because it's really hot on the inside, it reduces the energy loss through the casing. So we saved, over the lifetime of the engine, 16 gigajoules of energy. So we did aerothermal testing. As I said, Dresden do this for GE, for their actual engines. This is the setup that we used. It tested it through various Mach numbers. We got loads of sensors on there to measure the pressure, the boundary layer, the flow in the center of the volume, all that information, so we can go back and look at our simulation results and see where we're not getting things right and where we need to kind of tweak things. What information can we pass back to the science team that are working on the solver to improve their stuff to make it work better with air? It's a very loud test. I do have a video, but not here. It'll deafen everyone. So yeah, that is the overall design that you see there. They made this. This is 1 meter in diameter, completely made out of Inconel. So it's 100 parts combined into one. Mass reduction of 35%, system pressure drop 91%, so you need a smaller pump for the air. it met the 90,000 cycles fatigue test, the mechanical. 16 gigajoules of heat that was saved, and we printed it. So before we went for the whole part, obviously you saw earlier with those different design stages, we took sections of those, we printed them, we wanted to learn from it. You'll see in the first one on the left, we've got some lines, that's a recoater interference. Recoater is just hitting the top of a flat surface. It disrupts where the powder is, and then when the laser goes over, you end up with these lines, and then they're not desired. We did other tests like, can you get the powder out of this part? Can we reduce the distortions of the component during the additive process, and things like that. So yeah, we simulated it. This is the biggest simulation we've done. We needed quite a powerful machine to do this. Because 1 meter diameter, 1 meter by 1 meter 3D printers in powder bed metal didn't really exist at this point. They were prototypes. There are bigger ones now, but yeah, we simulated the whole thing. We took all the learnings from what we'd done before with our testing. We used it to actually inform us with this to do this bigger simulation, and we actually printed this first time. We did not expect it. This is the biggest part GE had ever made at that point, and it printed correctly first time. But that's the one you can see there on the right-hand side. Completely Inconel, completely metal part. So yeah, just to summarize, we start with design, we do simulation, we do testing, and then we try to learn from that. We all learn for science. For industry futures and for research engineering. Thank you.
Nathan, yeah, I just want to say that we are starting with the enabling technologies by Autodesk, and we are moving after Nathan to application. So that's the sequence. Yeah, thank you.
Okay. I'm actually usually kind of loud because I was a professor for a long time, so I was trained so that everybody can hear me. So so that's that. So I'm new to Autodesk, and one of the things that's so exciting is it's a company that builds real things. And if you build real things to be in the real world, there is physics involved. And one of the things that you see, like, you guys have all interacted with chat, Claude, you interact with these agents that are trained on massive data sets. And even when you talk about world models where you can just generate fake worlds, these are all deep fakes. Even our physics models are deep fakes of what we want for reality. But if you're going to put me in a rocket ship, I would like to know that I have a good chance of getting from point A to point B. That what you have in there are models that have been tested, are reliable, and so forth. And so the idea behind physics-informed AI, and part of what we want to do with AI, is really allow these AI agents to understand that there are rules, that these rules exist in the real world, and that you would engineer with them. So let me introduce the protagonist. Sir Isaac Newton. Just walk out of this door to, you could catch a train to where he studied, right here, and probably, you only have to wait like 10 minutes at King's Cross to get your next train to Cambridge, where a lot of the foundations of what we do today were laid down. And really, when you think about what Isaac Newton did, a lot of us sometimes think about physics, but I would say what Newton did is he invented a language, right? And that language was based on this idea of calculus, rates of change, and how to calculate that. Because once we had that, very quickly, we developed this language into amazing things. Now, I don't know if you know these equations here. It almost doesn't matter. In some sense, you could think of them as hieroglyphs, but what they are is relationships in the language that Newton developed. Relationships about what physics has to obey. And this was sort of a staggering, really started the scientific revolution for us, because now what we had is a framework to say, well, I know there's gravity, I drop something, it falls, but now you have a rule for how it falls. You know how you understand these things. We go from electromagnetism, all the electromagnetic waves that we do. So everything sitting on this phone, right, is run by those equations. Right? It's amazing. Look how compact that is. In this language, very complex things are just folded down to these small expressions. Fluid dynamics, quantum mechanics. With this, we did build this, right? Your life partner, right? You trade it out every 2 years, get an upgrade. But your whole life's in here, right? And that's the modern way we think about it. And now we even have all these super intelligent agents in there as well. So the question is, what do we make with this now in the modern world, where we have all this data? Well, when we do science and engineering, the hope is we can leverage all this knowledge we have, and that these relationships hold in our simulation world, and anything that we're going to try to build, we have to respect these things. So really sort of in some sense, the goal of this physics-informed AI is, first of all, can we leverage these relationships to engineer things that are going to actually work in reality? In fact, we're going to see some really cool slides here in a minute on buildings where we have these unbelievable architectural gems in the world that are coming out, right, for architecture. But at the end of it, they are living in a real world where the weight has to be held up, it has to hold up against wind. How do you get all that? Well, that's coming from these physics models. The other hope that we have here as we start using AI is that what we've seen with AI in large language models is we've taken the entire corpus of all human knowledge to train these things. And in physics, we often have very limited data. We don't have the kind of data sets you do for language or vision. So what we need to figure out is how to train great models with a lot less data. These physical relationships are what are allowing us to do that. Finally, you've already heard it from Andy, there's regulations. You can't just put up a building and do whatever you want with it. They're going to come and inspect it. And they're going to say, do you meet the requirements? That nozzle that Andy showed, if you're going to put that on an engine and you're going to get it on an airplane, that thing has to be certified. And of course, you're all happy about this because it probably means you're going to live. You're going to go from Heathrow to somewhere else, high chance of success, versus I don't know if this really works, and midway through this thing breaks. There's a lot of where we are is no fail environments. If a chat GPT prompt goes wrong and you just get bad information, nobody gets hurt. That's not the case with engineering systems. You have to get it right. No fail environments. How do we do this? We have to build these in. And part of what we want to do is build that into the Autodesk world. And so even when we come up with generative designs, for instance, buildings and structures, how many rooms, how we lay this out, these are sort of generative tools that we have at Autodesk. These live in a real world eventually. It's one thing to make a picture. It's another thing to say, like, yeah, but this has to hold a certain amount of weight, a certain amount of people. Here is its uses. Okay? And so part of that is what the story is around the physics-informed AI. And I want to give you one example of where this kind of technology, I think, is really needed. This is the Barcelona Supercomputing Center. It's very new, at least for science people. It's a really great building. Okay, so I always hold the standards to science people having a little bit less. There are lower standards when it comes to creativity, as you'll see in a minute. Like when you talk to real artists, it's like, oh, that's pretty boring. It's still a rectangle. Okay? But it's nice. It's got glass. If you're a scientist in there, you're super happy because you're in a nice building. But here's one of the architectural gems that they imagined for this. On the second or third floor here is this beautiful deck. And the idea was, this is where all the people come and hang out, have coffees and lunches, and guess what happens in Barcelona? Anybody who's been there knows it gets super hot, and this is right at the base of the hill. So around 11 o'clock, noon, it starts heating up, the wind starts coming down, and this is actually a wind tunnel. So what was supposed to be the architectural gem in this place where everybody's gonna hang out, nobody hangs up there. Because if you go out there, you're just getting blown off, right? So nobody has coffee there, nobody has lunches there. This is where everybody was supposed to go and hang out and have lunch. Nobody does. Why? Because when you built this building without understanding the environment you're in, or that it's not just forces, there's wind and so forth, you built yourself a building that actually failed in what you were actually trying to do, which is to create a space for people to interact. And in fact, that actually prompted this group, the Supercomputing Center, to start doing simulations of the wind flow over the entire city of Barcelona. This is exceptionally expensive. But this is the heat. These are buildings. This is the heat coming down from the mountain. And if you've been to Barcelona, you know how hot it is. And guess what? Sometimes you've engineered your spaces so that all the heat gets trapped. So Barcelona is as hot. It's now hotter and hotter, so you don't go in August. Barcelona's super fun, right? So it's always hard to say don't go to Barcelona at any time, but you don't go in August because you get caught in these things, and then you kind of melt, right? And then again, this is all something where in modern engineering and AI, physics rules, we can come to this and start addressing it. There are ways now to say, I want to now start thinking about my design. It's going to live in that space. How do I use the wind to help cool my building? How do I use the wind, but I don't create spaces where I'm putting people in like a vortex? And that is, in some sense, comes down to you still want to use these AI tools, but you now have to start respecting the physics it lives in order to do some interesting things with that, or at least be more careful about it. And again, you'll see some of these amazing buildings that are now being designed that are amazing, but they all respect physics, but you have so much space within the physics to create, which is awesome. So in other words, you don't still have to build rectangles to build, right? You can do really amazing things, but you also want to have this as sort of your back-end engine in the design cycle so that you kind of get this a little bit more correctly done. So that's what we're going after. Using physics, embedding it in our AIs, so it's a very smart agent. It has Newton capabilities, right? But at scale. Newton could only do pen and paper work. He had no computer. This can be like Newton with massive power, and so we're going to bring it to you. All right, I'll stop there. Next person up. Oh.
Thank you. So Anat is next. We are moving to the second part of this mini symposium, and it's about application creation. We're kind of consumers of math designers. We are using Autodesk software and other software to, and I think we are shifting towards a new reality now when we can, script and also create our own tools. Starting with architecture, I wanted Anat to bring the heavy, no compromise need for simulation and calculation, so maximum weight. Anat, do you want this? Or?
Yeah, I need this. I don't speak that loud. Okay, good evening. First, thank you, Assa, for the invite. Super excited to be here, and thank you for the 3 previous presentations because I think you really laid in a very exciting way what I'm going to talk about. I'm going to very quickly introduce our office, and then I will try to actually take you through the evolution of our... Oh, now you can hear. Yes. The evolution of our methodologies, trying to actually clarify how our design processes inform our projects and their constructability. And lastly, I will actually present one project a little bit more in detail. So this is us. We are now about 500 people coming from more than 50 nationalities, different countries. And we are divided to 3 main clusters, but we are supported by specialist groups. And their research is informing not only our competition entries, but also our build projects. So for example, Zaha Code, the computational design team, they mainly focus on engineering logic, then the sustainability, analytics and insights, which I'll elaborate a little bit later. We also work on the metaverse realm, of course, and the virtual reality, and we have on our premises a robotics lab. So here I'm just showing you the wide kind of breadth of our expertise, and the reason I'm showing is it just to actually express the sheer volume of questions that we need to ask ourselves every single day, whether it's an airport or a bridge or a tower or villa or a chair. We have to be very creative, and we have to find creative solutions which are tailored specifically to each brief. And the main, actually, let's say, parameter of the whole design process is the brief. What do you want to achieve? And the parameters are basically the climate, the location, and what the client wants, which is a brief. So gravity and creativity. Our relationship with gravity starts a long way back, and it's defined actually by defying it. So the first project that we actually built is the Vitra fire station, if some of you know. And Zaha introduced here the first kind of like huge cantilever. And I will just show a few more examples. For example, the port house in Belgium. In this instance, we wanted to design, we were asked to design the headquarters of the port authorities. And we decided to actually place this huge diamond on top of the existing fire brigade. This is a 110-meter long element. And the way to actually achieve this design aspiration was by collaborating with the structural engineer very closely. So we introduced here these kind of like protruding large legs, but that was not enough. It did minimize the length of the cantilever by kind of like halfway through, but we had to brace back that leg into the existing courtyard and introduce these kind of diagonal beams which are transferring all the loads down to the ground. And the next actually example is of a skyscraper. This is Lisa Tower in Beijing. And if you ever explored a floor plan of a skyscraper, you will normally find the core centrally placed because actually it does make sense. That's the most efficient way to design skyscrapers. In our case, we wanted to invert the logic, and we wanted to create a huge atrium that that will give another kind of like more poetic feeling to the space. So we achieved that, but actually splitting the core into two. There are two symmetrical cores that are binded and kind of like tied up with 4 mega trusses. Each one of them is spanning over 33 meters, and the whole system works in a unified way. It has structural integrity all together, the core and the trusses. That actually gave us a lot of freedom in the way that we could design our interiors, and we could give a really dynamic feel of kind of like ever-changing plans throughout the height of this atrium, which spans to the height of 195 meters. And another example is a layered vertical urbanism. This is a project which is under construction, Tower C in Shenzhen. The tall tower actually reaches 400 meters. And in order to actually create a more human-centered design, in that sense, we wanted to activate the ground floor because the scale is just not human. So we've done that actually by kind of carving out in the massing of those towers and introducing those steps rising up, allowing us to introduce all kinds of like buzzing activities from the street, retail, landscape, gardens, places for people to stay. And design optimization is not new to us. It's part of our normal day-to-day work. And in this instance, you see a core study. So here we're exploring different positions of cores in relation to different actually floor plates. At the same time, exploring different opportunities for facade designs. And on the left, you see here just a few of those exploration. At the same time, we are looking at floor plates which are really irregular, like the Soho Galaxy. And with the help of the Analytics and Insight cluster, they are analyzing the position of the desk in relation to the facade, how much daylight each one of the employees receives, what is the distance to the entrance, and what are the levels of interaction between the people in the public spaces. So all this information feeds into our final design, and of course the beam with the Revit that we're actually working on complex buildings and trying to integrate all required system, including mechanical engineering, of course. And in terms of performance compliance, this is a project much larger, 70,000 square meters in Saudi. It's a research center, and the architecture was actually kind of following a very strong structural concept, which is a hexagonal adaptive field. And it not only gave us advantages of being super compact, but also advantages of energy preservation, which is super important in the climate of the desert. As you can see on the right, on the bottom right, each one of the hexagons was designed as a wind catcher. So it kind of like scoops in all the wind and cools down the external courtyards as well as the other internal areas. And all the massing is placed kind of like in orientation towards the north in order to maximize the amount of wind that cools down the whole complex. And construction efficiency. We're looking here at Bea. This is the smaller project, 9,000 square meters in Dubai. And here I'm just going to talk about one aspect of it. As you can see, it's the geometry is super curvilinear, millions of double curved in, let's say, in theory. In reality, the way to achieve it in a, let's say, in budget, in time, in schedule, was actually dissecting the whole geometry to a grid of 2 meters. And cladding it with only flat panels. So this geometry achieved with just GRC panels, glass reinforced concrete, to somebody who doesn't know. So it was super efficient, but the result in terms of design, I think, is quite spectacular. And digital fabrication. So this is a bridge designed by Zaha Code in collaboration with Philip Bloch Group from ETH. And this is a really interesting bridge because it works by compression only. There is no glue. It's 3D printed concrete that actually works by friction. The length of it is about 17 meters and the height is 3.5. And it can carry up to 90 people. So try not to be the number 91. We also look at material innovation to new form, new structures, and swiftly shifting to the AI. I think a lot of the introduction was already given, but just to say that it gave us a huge boost of creativity, but also a huge boost to rationality and to intelligence. And when we work on complex projects at the scale that I have shown, there is no room for regularity. Actually, we desire irregularity and differentiation, but they all have to, all the different conditions needs to resonate and kind of like come together and collide into one unified, let's say, system. We are working and trying to understand the world of 3D design, generative AI, because it does actually help us to simulate and to try to understand if we can achieve our design ambitions in this way, in a more efficient way, in a faster way. I would like to add that at the moment, I think that existing tool can assist us on a portion of the process. We can elaborate later on that, but not on the entirety of it. And the last project, I want to actually kind of clarify again that we always develop a system from macro to micro. We look at it holistically. And the project is in Macau. This is 150,000 square meter hotel. And this is the first free-form exoskeleton steel structure that was built. And it was, the methodology of this was actually of a comprehensive collaborative 3D model that not only tested and analyzed the structural integrity, but also rationalized the architectural geometries and manufactured the facade components, which obviously had to be rationalized as well. And the underlying diagram is super simple. It's actually two cores connected in a podium, in a few levels of podium, and two bridges on the upper levels. And there's a system of slabs and a few internal columns wrapped up in a cladding, and externally the exoskeleton. The exoskeleton actually gives us a huge amount of flexibility in terms of designing the floor plate, and that is a huge advantage in terms of the client's requirement. So these levels of podium allowed us to actually open up the lounge into an atrium. That atrium spans over 40 meters high, and it allowed us to create some sort of a special event as you enter to this building. It was super important for us to actually create these visual connections, penetration of daylight into this space, and also understanding the three-dimensionality of the space. So on the right-hand side, you're actually looking up towards the belly of, or the soffit of the bridge. So you experience in and out all together, and as you go up the panoramic lift, you're passing through internal and external spaces. The first part of the design process was the structural optimization, of course. So we started with the structural engineer, analyzing the structure, dividing into families, defining the rules of each one of them, and the node family. And the most important one was the vertical load distribution. This actually diagram on the right really defines not only the structure, but also the architecture, because this is the most efficient way of transferring load through the facade. And just to give you a bit of sense of scale, most projects ask for a mock-up on site, and this is the most complex node, the doubly curved one, and the height of it is 70 meters. And just to finalize, again, we try to develop our language that it will work holistically from the facade, the structure, interior design, and to the level of the furniture in order to create a rich and intriguing human experience. So you will see it here. This is the restaurant on one of the bridges. And the pool on the top. Thank you very much.
Thank you, Anat. Please, everyone, some of my students are disappearing. Write some notes, because it will be nice to have a big discussion at the end of it. So thank you. I think you demonstrate the volume and the need for what actually the two Andys were talking about, the durability and the Andy and Nathan. Yeah. So I will show some, only 3 projects, but before I saved very old renderings for some friends that are in the building. Sia, my old business partner, that actually worked with Tony. I mean, in the old days. This is 20 years old. Sean Hanna as well, that is here with us, architect. Up, we need to up. Yeah, okay. So this is just really quickly. I will run quite quickly through some images, but this was one of the first time where we use a little software called, at that time, Complex Matters, later within Lab, developed by Tony and Sia. And it was just placing units within a voxel grid based on stress loads. That was the promise. And this is how we actually all met 20 years ago. So I found this picture that was kind of a messy rendering from one of the simulations. But I loved it because it was so real. It showed the vulnerability of the software. So I really love that little thing. And this is just a few old slides from there showing the voxel grid and so on. The Osteon chair. And what's nice about this is that you can say that it was the first time to actually bring in the notion of infill. There was no infill before. See, I don't know if you, at that time, I don't think we were aware, but there was no infill. So this was really the first infill, basically structure growing from the inside of objects, not around objects as support. Still actually quite clever. Yeah, so goodbye. It sits in a nice museum. Actually, it's in Barcelona Design Museum permanent collection. So at least, and the stool is, I think, in the Red Dot Museum. So they sit in nice places. I just wanted to talk about, take a moment to talk about where we are in history right now. So this is resonate with me very much, that moving from information age to imagination age. I think as designers, we experiment. We sometimes talk to engineers and calculate things, but most of the times we experiment. And we reflect and we go to the next permutation or iteration. And I realize how valuable it is actually today. So for all of us to actually use that methodology when working with agents. So that bottom line is really interesting. So creative currency coming from imagination, knowledge, gain, experience. And I would like to call it H to M to H, which is human to machine to human, kind of industrial loop. M to M, machine to machine, is an old term now, actually. Machine to machine communication. So machines that talk to machines that talk to machines. These are the forms of production: form, pour, cut, join, finish, grow, additive. And now we have a new currency because we work in virtual environments. So we work in virtual environments and we materialize using some digital tools. So that's a slow shift in paradigm. When I chatted with one of my agents, I said, would you like me to generate an image, a diagram? I said, yeah, go ahead. So that's the diagram that is not well designed by me, not by me, by the agent. We're moving from mass assembly lines of repetitive motions into very quiet production farms. This is, again, a failure that I love to keep from an old project for the famous tool that today you can see today actually in Fusion you have a similar approach. That was with Altair a long time ago. Using, again, stress loads to actually vacuum out or remove material. I'm showing this object because the math kind of took us towards bone formation and why bone look like bone. So if it's a little bit of a kind of a natural selection fast forward. Some of you know this project. I'm not, by the way, it's at the Design Museum permanent collection now, so you can see it there. Sorry, I'm not showing off things, but you can, I don't know why I mentioned that. But for me, the interesting thing here is that bone, the math took us towards bone formation. This is another project from my collaboration with KIT, Kyoto Design Lab, looking into the microscopic landscape of the bamboo, the way bamboo grows. And what we did here is that we used CT microscopy to basically study geometrical topologies of the natural microstructures. And then, of course, making it into 3D and producing some samples, and creating a generative process that mimicking the bamboo kind of biointelligence, let's say. And the basic proposition was that we only use cylindrical form, so it's empty and very, very lightweight. So it's kind of hollowed infill, if you like, but smart in some way. Why is it interesting? It's interesting because it reduces material consumption for kind of minimum, and so is energy as well. So it's like trying to, again, hold weight with minimum material. So same old kind of exercise. A nice quote from Darwin. And very quickly, going over to one of the latest projects that I think is relevant is a digital twin footwear that is inspired by nanofibers, the way leather is formed, actually. And leather is a consumable good, but the epidermis, the human epidermis was one of my inspirations for the project. And here you can again go back to the old microstructure, but it's collagen fibers that are growing to perform in a certain way based on natural conditions. So sweat, humidity, gravity, expansion, and so on. And in this project, I worked with Stratasys, and Stratasys are one of maybe the only company to really go to produce multi-material, like real multi-material, multi-density, multi-color, multi-opacity. And if you have that manufacturing technique, then how do you work with it? And the interesting, intriguing thing here was, or the challenge here was, to create a full living digital twin that understand physics, understand forces, but also get sensor data streamed live from the physical object. So if you work with the first generation, you send information to the second generation in the cloud. So in this project, we build up a very quick mock-up of a physical environment for the digital twin that takes sensor data into some modification and generation of objects. So the particles were just, I don't have any animations here because I do have a lot, but we don't have too much time. So the particles are just shrinking and growing. They're full of gel, so they're gel particles. We have 1,000 particles inside. They start as 2 millimeter, and they just grow under your foot. Some more examples of multi-material and print on fabric. But the interesting thing is that there's an age for the product. So the product has an age and a generation. So it's, in this case, Gen 2, and the age is 733 days. The basic proposition is that with time, objects will improve, in this case, in the virtual reality, of course, or the virtual environment. This is the first good prototype we actually fabricated after a lot of experiments. In this case, we only had 5 different materials, and like a translucent rubber going wrapping around the intricate network of multi-density fibers and gels. And of course, the fibers are supporting your pronunciation, your pronation, how do you say? Yeah, and the gels are supporting your basically a cushion, like bespoke cushion. There's also air knobs for ventilation and so on, and the object from the sensor matrix learn as it grow, basically. The white is a conductive circuit board filled with silver, so silver field. So it means that it's also looking into, this is a full prototype of photography with no electronics, but the sensors are actually mimicking at the moment the position for the sensors, but the sensors are, in the real model, are fully functional. So there is, in this case, humidity, heat, and pressure sensors. And of course, here you get the full spectrum of the machine color, like CMYK. So you can reach, when you have full color capabilities, how do you deal with that as well? It's like, it's not very straightforward. I realized that 3 colors are easy to control, 5 colors are easy, but 200, very difficult. Yeah, that's it for me. Just to sum it up, the big question for me is, if we have that capability of simulating in virtual environments a digital twin, testing, growing, improving, and then fabricating, that we can maybe say adding the element of time to the design process. So rather than just say, okay, this is the best outcome, let's go, architecture can study for several years for the next building to be improved nearby. So as of course, footwear is a good yeah, just one last phrase from me, from Noam Chomsky. Claiming that a machine can learn is like saying that a submarine can swim. It's an old slide again. Maybe some of you have seen it before, but I love that phrase. So thank you. And we are the last but not least speaker is Andy Lomas. I love Andy's work. And Andy is celebrating all the capabilities, all the tools and the technologies we have in such a wonderful, free way, So sometimes without, gravity, you're using gravity as a brush in a palette, but not necessarily as a constraint. So thank you.
Okay. Well, sometimes as a constraint.
Yes.
So okay, got the clicker. Cool. Cool. So, yeah, I guess what I'm presenting is maybe a bit more speculative, a bit more, I guess essentially it's an art practice that I've been developing over many years. Though I actually come from almost like a mathematics and then sort of animation and graphics background. But I've been developing this art practice for many years, which has started to use more and more in the way of things like machine learning and I guess AI sort of technology, almost to help, almost as a way of not doing generative AI. It's not that the final images that you see on screen are creative, like using things like Midjourney, but how to find the rich, interesting, complex, the things that almost like the core things I want to discover through my practice. Machine learning and AI has started to become almost like an essential tool to allow me to, as I put it, work with even more unruly systems, almost like be more adventurous as a creator, as an artist. So almost like, and I guess this is almost a version of, maybe it's not all physics-informed AI, but it's almost systems-informed. That it's always what the AI or machine learning is being used is to drive another system which almost provides a ground truth. So a bit like a physics engineering simulation. What I'm doing is essentially more like biology simulations. So I'll actually sort of start showing one of my videos from a few years ago. This, basically, what I'm fascinated by is almost like the things you see in nature, things that you see from living organisms. They're sort of crazy, rich, organic complexity, but also it's complexity with meaning that you see in natural forms. Thinking about what can be the processes that those could have come from. So rather than just thinking almost like looking at the top-down structure, thinking, okay, how is this created through things like processes of cells interacting with each other, cells growing, almost like the biological processes. How do these forms and structures emerge from those sort of systems? So what this is this is computer code that I've written, basically simulating cells growing. So there's all rules about things like cells need food to grow. Food can be created by things like light rays hitting the cells, almost generating, so it's all simulation. It's like light rays hit cells, generates food. When a cell has a sufficient amount of food, it splits into two cells. The cells exert forces on each other, I guess Newton's sort of cell forces. So basically, it's all basically rules creating a behavior, which I'm hoping, if you get those rules right, and almost like parameters of the system right, hopefully it's going to make something surprising, emergent, richly complex. Most of the time it's probably just going to go wrong. Most of the time it's just probably just going to sit there doing nothing or blow up into like, sort of like go out of control. But hopefully if you just get the balances right, suddenly really, and I want them to be surprising things happen. And I guess what it is, all the movement, all the form, everything just comes from these simulations. So basically it's how do I discover the simulations? How do I discover the combinations? Almost like it's a synthesizer of form and movement. How do I find the parameters that make the interesting stuff happen? Sometimes I'm sort of thinking about more physics-like things. This is almost like what I'm doing is then trying different rules, trying, like recode things. Let's try, learning by creating systems, then let's reprogram it in slightly different ways. So one project I did was trying to create 3D printable vase-like structures. Actually, let's make something that is actually fabricable. And one of the main things I think you all know that with limitations with most 3D printing technology is that if you get beyond a certain overhang, things become difficult to print. Either you can't print it, or you have to put lots of support structure in there to allow it to. So one thing I thought was, okay, well, let's make that part almost like an influence, a nudge in the system. So let's say that as you get to beyond certain overhangs, that can affect the growth rates. So basically, there's various different things that can influence almost the environment influencing the system. So it's not trying to be like a strict engineering, the system where everything will be 3D printable. It's just saying, if we've got influences such as overhang angles being able to affect the growth rates of the system, or maybe that means that in certain places in this, almost like the palette of possibilities, you've got structures which are hopefully richly organically complex, but are also naturally 3D printable. So to be the honest part of this, I went through quite a lot of iterations, quite a lot of things that really didn't work. But after a few sort of trials and errors and findings, I managed to get sort of things which were like this, which are hopefully 3D printable, but still being hopefully intriguingly complex and rich, and also maybe being quite structural. That they're things with lots of grooves and forms, which actually means that maybe they are actually almost like surprisingly strong structures, like lots of things that happen in nature. And these are, luckily, saying genuinely 3D printable. So these are some sculptures from exhibitions. This is actually from an exhibition at the ZKM. And I guess one thing this also shows that when I'm presenting this, I'm often trying to tell the story of the process as well. Trying to have, hopefully, these vase-like structures, which hopefully are intriguing sculptures in their own right. But there are also things in here like animations showing the simulation running. A number of forms which are almost like a sort of developmental sequence, going from almost like the initial egg-like sort of state to almost like gradually getting to more and more and more cells, more and more so rich. So there are things in there which, if people are, are intrigued to read, hopefully starts to tell the story behind them as well. Because there was so I'm going to say one thing, say, the process these are created by, that these come from this almost simulation of biological rules, is important to me. And part of that is that it's a process of discovery, finding these things. So I guess this is where things like machine learning sort of starts to come in. So the backstory behind a lot of what I do is trying to find ways to help me navigate that space. How do I find these forms and structures? How do I tweak the parameters to find the interesting stuff? So a lot I've been doing is writing this sort of system called Species Explorer over many years. And one part of that research we did a few years ago, almost like addition to Species Explorer, can actually do lots of different methods for almost like different ways of exploring, creating different parameters and trying things out. One thing we tried out a few years ago was some research together with Professor John McCormack and his team, and Dilpreet Singh down at Monash University down in Melbourne. And basically we're looking at, could deep neural networks be part of the ingredients to help explore these spaces of possibility? And we came up with two different things that actually really significantly helped. So one is that when I'm actually generating these, when I'm using this Species Explorer, is almost like rating and categorizing things. I'm doing lots of tests, then I'm saying, okay, I'm going to give that, I'll go score that a 2, I'll give that a 3, oh, that's really interesting, I'll give that a 7, oh, that's a 0. So basically I'm sort of scoring, almost like subjective ratings for things. But also I can categorize things. I can say, oh, that's maybe like a broccoli, that's like a brain, that's like a lung, that's like skin, that's like cabbage, I don't know. But basically starting to name and categorize things. And then that sort of almost like provides me ways of almost like understanding and navigating the space, and also tools to be able to do things like, I'm often interested in transitions between states. So it's things like saying, well, is there something that almost allows you between cabbage and brain? Maybe that's going to be sort of where the sort of hybrid, liminal, interesting things happen. So the other thing we managed to do with the deep neural networks was also do that almost really quite directly. So this thing is much more interesting, where basically this is using a deep neural network to predict at new places in this parameter space what it thinks from having done, so I maybe run a few hundred tests, and it's starting to be able to predict with new parameter values what type of forms and structures would it create. So what you're seeing here is almost like in a chart with, laser pointer does work, great. So there are various categories here, like animal, balloon, brain, mess, no growth, plant, worms. And basically those have been shown different colors. So this is showing what's like a slice through the parameter values, where the deep neural networks now saying, okay, based on all the samples we've seen so far, it's predicted with these parameter values it's going to look balloon-like. These parameter values are these light blue sort of brain-like things. These are the animal-like things. And also, it's showing where it predicts they're going to be transitions. So that it's almost like, as we're going from the red area to the light blue area. In that transition, it might not be right, but that's where it's predicting there's maybe almost like a tipping point between one behavior and another, which is where I think there's potentially particularly interesting things might happen. So then this is an example of me using this. So this was a series where I was trying to, well, I guess I sort of generated quite a few forms and started seeing these almost like interesting root-like sort of structures being created. So I started, as well as scoring, just how much I like things, I started scoring how root-like structures were in there. And then the deep neural network could then basically try to almost like optimize that, try to almost like suggest points in the parameter space to go to where maybe it's going to be even more root-like. So it's almost like, let's accentuate. There's this, I didn't deliberately program it to produce root-like things. It's just started doing it. That's cool, that's fun, that's interesting, it's surprising. Well, let's lean into it. And almost like machine learning almost really almost like helps me do that. Even though I've got too many parameters to get my own head around, by using a machine learning algorithm, I can start to make it more and more root-like, more sort of rich, complex sort of organicness. So one of the things, it's almost like it's a real assistant to allow me to work with, as I put it, even more unruly systems. Be, I think, like braver in what it's like these sort of systems, I think, produce surprisingly complex, interesting things, but they're also just like really difficult to work with. Oh, cool. Well, actually, the machine, the computer as well, can help that side as well through things like machine learning. So, and I think just to end, what I'm going to show is a recent piece. So this is a simulation based on actually what's called social amoebae. So there's these real world creatures that almost like coordinate behavior with each other using chemical sort of messages. And this was, as a musician, Max Cooper, who I've been collaborating with for about 12 years now. We've done quite a lot of projects together. So this was from a concert actually just a month ago. That's Max down the bottom. And this is actually over at the Royal Albert Hall. So this was the first time this was publicly shown. And it's basically, it's actually a music video, but it's basically 13 million computer simulated social amoebae doing almost like going through this journey through lots of different forms and structures, which, yeah, almost like a journey through the sort of possibilities that their algorithm can emerge, things can emerge from. So I'm going to switch to the video. Sorry.
see. Wow, that's amazing. So thank you so much. I think that piece will be part of Max Cooper's new album.
It is, yes, yes. It's in his new album, and he's currently on a tour. Show, that's part. That is the opener for his set, his new tour.
That will be released soon, actually. So we're all looking forward to Max Cooper.
Not yet publicly released as a video, hopefully coming soon.
Yeah. Thank you for all the speakers. I was thinking that we can maybe open just a discussion, a grand auditorium discussion. So if I can ask you please to sit. And I also wrote myself a few questions. If you will be a bit quiet, but please don't. So Neil, maybe you can you help us with? I think there is a catch box. Hello. Yeah.
Okay.
What's your simulation?
Thank you so much. Hello. Yeah. All the students, leave a question before you go. No questions? Let's start with a guest. Do you have any question for anyone?
Thank you for sharing, knowledge, and I was wondering maybe what's your thoughts on laziness with future designers or the reliance on certain types of programs. Just because I think maybe a lot of people are studying design, or I was wondering what your thoughts are about that subject.
Laziness, Tony, you want to start with?
Well, I mean, so I'll just say, I guess laziness, it's not strictly a thing for just design, right? It's, in solving a problem, whatever it is, so, designers will be solving a problem, software engineers will be solving problems of sorts. It's all about the passion to find out how to do something and to do it well, right? To achieve a solution to that problem. So even as, say, AI-enabled tools deliver a lot of automation and can simplify a lot of things, I can speak to software engineering because that's my profession. The notion of implementing, like writing that C++ code, is becoming irrelevant. It very much is. But you still have to think about the problem you're trying to solve very carefully, experiment with multiple models to see how you can write code with them, and then verify the outputs. So you can't really take a step back because, the more you get into this, the more you can actually do, the more you get actually exhausted by it, right? So I don't see laziness. I see more, if you dig in and begin to solve very many problems, what will happen is actually the flip. You won't be bored. It's going to be super exciting and energizing. There's the initial it's scary because it's writing the stuff I used to be able to write myself, and I was so passionate about writing all this code. Now it's doing it so well that I don't have purpose, but actually you do, because you were always writing code to solve a problem. Some of what Assa was showing, like the early days of complex matters within, those lattices, I wrote the code that created those topologies, and working with Sia, to try and I was trying to do what Sia was doing on his doctorate study, right? But writing software that can do this. That step of writing software was just a way of implementing a solution to a problem. So I say, in design, you're solving problems as well. And I think, yes, there's automation that's going to help and make that faster, but it just gives you more capacity to do a lot more stuff, right? So I don't know if that answers your question, but that's the way I think about it.
Yeah, so something for me to think about is when you're going through that kind of design process and you're trying to use AI, it becomes it's another tool really to help you, and it can also help you discover new things. And when you're going through that process, you've kind of got all these variables, and you tweak this little thing, and this other thing happened, and you go through a lot of what Andy was talking about. Like, you can discover a lot of new things, and it's true for generative design. It's true for AI tools. If you just point at AI at something and just blindly accept it. I think that it's going to give you an answer, but if you don't really understand the problem, or you're trying to not apply it in a creative way, then yeah, that can be lazy, but you can actually get a lot from it when you actually work with it and collaborate with the tool.
I can just say that our students are the opposite of lazy with these tools. So it means it's amplifying the speed. It's just outstanding. So it means, Alex, how many hours do you sleep yesterday? I mean, so it's exciting. It's exciting what we can achieve at the moment. So that's my little take on the laziness.
Yeah, I mean, one thing I'd say is that there's always a story that keeps on happening of new technology, things come in, where often the justification for them almost spending money on them originally is to make existing processes faster, cheaper. But the much more interesting thing again and again is, what does this enable us to do which we couldn't even think about doing before? I mean, the lazy thing will be just like, okay, I can now do the same thing, sort of what we used to do, but it's 1/10 the cost. And everyone else can do that as well. But pushing it, looking at the tool, saying, what does this allow you to do? Reach the stars, basically. I mean, then I think that's the human instinct, is that, it's always people striving to move beyond their expectations. That's where interesting things happen. And I think these tools just allow you to do that even further. So when I say my stuff, it really does feel to me like it allows me to be braver. I'm obsessed with this stuff. That's why I do it. I'm not being lazy. I mean, there are opportunities that these things offer. And that's so much more interesting than just, hey, we can do the same old stuff, but cheaper.
Just about this topic, if you ever thought to be an architect and you think you have some laziness in you, just choose something else, even in the AI world. I think that from our end, I mean, all of the above, but what I'd like to say is that what is super exciting now that we can actually verify the result. So we can actually test it, and it makes it not only faster and cheaper, which is obviously super important for our clients, but also more efficient results. So we can be as creative as we are, but we can actually, in a way, we also use the word product for a building. We can actually sell a product that is more reliable, because risk assessment is part of our life. I mean, we just live it. It's part of our contract. We cannot actually risk, in a way, any aspect of the building. So that allows us to deliver buildings in the way that we want to deliver them and explore more opportunities. Yes, we do have to take decisions and find ways to actually take decisions in a better way, in the sense that the opportunities that are opened up are so wide that actually the selection process is more critical now. And I believe that still the human judgment is important here, because I think that, if I may say, correct me if I'm wrong, but I think that still the tools that exist, they can give us maybe, let's say, even not yet there, the structural verification, but they don't combine the design actually, or the aesthetic, let's say, parameter. And yes, I will get a really good, reliable product, but it doesn't know what I'm thinking about, how I want, or what is the sense of the experience that I want to give in that building. And that is the leap of our work. So,
if I can ask Nathan, in relation to this topic, what we see kind of two things. We see the yearning for the magic, like the magic tool, both from the designer side and the business side. So it's been, I think, I don't know if you agree with me, but selling that magic, complete automated solution was always a big promise. I mean, it's automated, it will do everything, yeah? Versus solely working with it. How do you see that?
Yeah, so, I mean, for me, what I think about in all this is it's the acceleration what you can do. You know, to your point about the aesthetics, so one of the reasons Ferrari is because it's not only an engineering marvel, but when you look at it, it has an impact. Like even if you don't like cars, you're like, that's a work of art. So Ferrari has understood this balance between art and performance. And imagine being able to design such an art object in not 6 months. Like you're getting there in like much faster, weeks. So then in your 6-month cycle, think about how many more designs you can come up with. So I feel that ultimately what AI tools do for you guys, I mean, you guys are the big beneficiaries of this. So and by the way, on the laziness issue, I've noticed from, you know, I came from the academic world, there's a concept of conservation of laziness. It's just that they were lazy in different ways throughout my whole time. And of course, there's going to be lazy students here. But for the people who realize what they have as a tool and what you guys, we never had access to tools like this, right? I mean, it's amazing what you have access to and if you can capitalize and learn how to use it to your advantage. I mean, it's unbelievable what can be achieved. And then now your imagination space can be much richer. Because before, it's like, I don't have the tools to really do something. And now I have a tool that allows me to go so much further, so much faster. I mean, I don't never really wish to be younger. I think, you know, one life is good. But sometimes when I see some of this, I wish I could see where this is going, because I just think it's going to be a transformative part of humanity, right? We're talking something much bigger than, you know, we're doing designs, but really what I think is happening is we're going to see a bifurcation of what it looks like to be human here, right? I think.
Just to encapsulate it for a second, bring it into design process, design thinking. Kevin, I don't know, what do you think, if you want to take part in the conversation? But we are working in iterative design loop. Okay, so the H to M to H is also a design sequence. So it means we are putting human judgment. We work with a machine. We apply human judgment. We go back to the machine, and I really see that as an excellent way of moving forward and developing objects.
Just okay, you can. Thank you very much. That was actually really a great overview of enabling and application. Something that really struck me was particularly closer. Okay, better. Okay. Something that struck me was that something that Andy Lomas said in his interaction or collaboration with these deep neural networks is the application of intuition and kind of visual categorization. You spoke about leaning into something that the system was doing. And I was wondering whether you could kind of elaborate a bit more about that, because that sort of collaboration with the AI and that system that you're doing is, I think, something that's not very much talked about. And then I was wondering what you other people on the panel think about sort of, you know, what is your interaction? What is your feelings about that?
I guess me being part of the loop is utterly essential to me. Reason I'm doing most of this is because discovering things, being part of the process, you know, the moments where, you know, things do stuff that I just, you know, because completely unexpected, and then make me think about and understand things differently and go off down new avenues. That's, to be honest, that's the real things that motivate me. The idea of automating that out of the system. Well, why would I do that? That's going to make all sorts of just pictures that I'm not involved in anymore. So yeah, I think that's absolutely, it's for me, it's really important. And a lot of the research I was doing with John McCormack, that was specifically what it's about. It's almost like, can we use things where we're specifically training it against my own aesthetic preference and my own categories, and ways of being also that I don't have to build too big a training sets. A lot of it was about like, how can we make the training really efficient, so that we know we can see where the training's not working and almost minimally retrain it to make it something that helps me to make my own trained model very efficiently. So that it helps me rather than me having to spend months training this thing and then it actually just produces really boring results. It wants to be an iterative process of, it learning my aesthetic preference and training. So that was a lot of what that research is about, and I think that's also what makes it feel like it's it feels like a real collaboration. It feels like I'm be able to change my opinions and change my directions and explore things in a much more agile, iterative sort of way. So there's also one person I worked with many years ago, very wise mathematician, who basically said that if what you do in these sorts of systems is just come up with a fitness function and then let it run, that is always just a good way to find out why you've got the wrong fitness function. It never isn't, and also it's just never satisfying.
Then we have another question.
I'll just respond to, just again, software engineer talking about creativity. I know it's hilarious. But so back in my younger days, I used to love graphic design. I mean, I still do to an extent. But I read a lot of work by David Carson, who's a New York-based graphic designer. And in one of his books called Second Sight, he talks about intuition and the notion of being able to teach graphic design. But in the class, he'd try and get the students to get to a point where it felt right. Because everyone's got a sense of what feels right to them. What Nathan was saying about we will now see the human experience emerge in a sense. And I think about my experience writing code now with LLMs. And Codex will do something slightly different to Composer, will do something different to Opus, whatever it is. These are just different models. But I've developed a sense of taste of what Codex will do. I describe it as a maverick, but it hits the nail in exactly what I wanted to do in a specific situation. But that's my preference, right? I talk to my team, and they all have their preferences and ways of working. But in a way, this is actually an expression of your own individual human creativity. Knowing when it's just right, this is exactly what that is. And so this emergence of the human experience becoming what we are now seeing is actually, because of the non-deterministic nature of AI today, it does open up creativity in a whole new domain. Like it's like you try the same prompt in different systems, you'll get, or even the same one, you will get something different each time. Slightly different, but it's different. And one of these things will be the one you like, and that is your preference. So to me, that's a very interesting domain now, because the old way of writing code was like you had a problem to solve, you wrote very specific code, it was very precise. It was highly optimized, as the Pro S, whatever, C++ guy, and then you got the thing you wanted. But you couldn't get anything different to that. It was exactly this. But now it could be completely different tomorrow. New model comes out, you don't get the same thing again. So it's like, I'll finish by version control. What do you upload to get saying this is the thing I can commit as a version? Because tomorrow I could attempt to regenerate. It's going to be a very different application altogether. So what are we versioning now? So anyway, many thoughts, but I just wanted to at least express that.
Thank you. I'm really interested in caveats, but just one to respond to what Tony was saying. Tony is speaking from computer science, working with human-like agents. And we will see very similar, we are already seeing very similar interaction with these agents from the design side, from the creative side. Very similar. It's natural language, right? So we're moving into natural language. I'm just wanted to highlight that.
Yeah, following on from that, really. Yeah, thanks for all the wide range of presentations. Fascinating. But my question is around these tools' impacts on process and kind of team capabilities, if you like. So in UX design, there's a really interesting discussion going on about, maybe we need to challenge the traditional way we designed. The double diamond kind of goes out. Sketching maybe isn't so relevant anymore, and wireframing, we just vibe code up some high-res working prototypes almost immediately. So there's, and that discipline of design AI is potentially kind of not ripping up the rule book, but radically changing the way the design process could happen. And I'm just interested, particularly Anat, but all of you, how's it changing the way you work? And how's it changing the way you think about the teams you need? You know, what kind of skills you need in your team?
Like human teams or? Complexity.
I think I'm a little bit of an odd bird here, in the sense that our actually doing is very different. So in many senses, the team, let's say the team structure has stayed, let's say in the last 2 years. I mean, things are changing very quickly. But the numbers of parties that we need to collaborate with are reducing. So it's not that dramatic because architecture as an industry has always been slower to pick up because we are, I mean, specifically in our office, obviously we are trying to push the boundaries and we rely a lot on technology, but we also rely on building permits, right? On planning permissions, which take forever. So we look at the process as a whole, I mean, until I have it built, when actually the real physics come in, because until it's built, I mean, I'm not actually testing it in that sense. But I think that for just a quick example or simple example is that we just minimize our work with vendor companies. We do everything in-house now in literally, I mean, days. And now we collaborate with companies like Xfigura, if you're familiar with. I mean, then it's not only just a huge pool of image-based kind of like environment, but actually we can very quickly get the mesh out of it. So we have the model. And before I used to actually ask somebody to model something. It would take maybe 2 weeks to get something really complex and rationalized. Now I just have it. And then I can change it very quickly. So there are certain platforms that actually have all the, let's say, all the design stages kind of like combined rather than picking up tools, you know, all together, and there's no coherency. So the more the platform allows us to run from ideation to, let's say, a model that we can start working on and developing with, I mean, that's a huge advantage for us. And I totally agree with Nathan that I don't think that it's actually, let's say, I'm saying that basically these tools allow us to explore more and more. I mean, I'm a person that graduated doing my thesis in rapidograph, if you know what is it. So I was literally drawing the lines, and now, I mean, I don't use AutoCAD, or sorry to say, but yeah, but we use Revit. It's okay. So, and Maya. But in that sense, our tools changed dramatically through the years, and I really don't miss those days. I think that it just allows us to explore more and more, and what I could actually imagine when I was drawing the lines, it's nothing like what I can imagine now, right? I mean, it's just exponential, and it is changing day by day. So please develop something that that works well.
From Sean, professor for architecture at Harvard, a good friend.
Could I just say just one quick comment on my team size, which I used to work in visual effects and animation, and I guess actually the animation industry is one interesting industry where you have projects with huge numbers of people, and also projects with just like individuals, like lone animators, and both being able to like almost achieve the highest levels of sort of work. So a big differential. I mean, I worked on Avatar, where we had 1,500 people working together on that project. And I actually gave a presentation to SIGGRAPH about it because I was presenting my own work by myself and work, which we did on the Avatar with 1,500 people. And what is it that's different? And the big thing is control. It's almost like if you want to be able to utterly control everything, that's when you would need a bigger and bigger and bigger team. And I think that's one thing that's potentially changing a bit with this technology. I think that you know, some of these things are the things which will enable maybe a smaller, maybe, you know, a team of 100 people to do what a team of 1,000 people could do before, if you want that sort of level of control. But there's also the opportunities for the, you know, the more individual, very, very small teams, where I think what they're going to be doing is just pushing far, far further. Being able to do that is almost like, you know, really small, you know, creative, you know, which are generally just like a very small number of people working together or individuals. I think they're the people who are going to be really just pushing out, enabling them to, you know, to do more. Yeah, do things they could never think of before.
Just to add something to this as well, we talked about, you know, investors are normally a bit nervous in investing in single-man startups. Now we see startups like single human working with 5 or 10 agents. How do you work with that? Obviously, a human can, you know, be a bit ill or retire quickly and say no more. But so that's a really interesting one. Yeah. So, but I mean, scaling up, amplifying human capacity. I think this is where we are more or less. It's not replacing necessarily. It's amplifying. Yeah, there's something to do with UX that I really am very allergic to, because at the moment the 2D generative AIs are working in silos. I don't know if you noticed, but they constantly they work in like banners, and they don't have an holistic view. They constantly think in like bricks, almost Lego bricks, like units. Yeah, so that's still a problem. Another little thing, thank you, Andy Harris, for your presentation, because we all know in industrial design the challenge of intricate parts talking to other parts, you know, inside, outside, shell, and so on. We're talking about physics-informed AI. It's not a 2D thing. So we are entering into a whole new layer of challenges with and realities with physics-informed AI. So it's full 3D understanding and so on. We're not there yet, but that's really interesting. Sean?
Yeah, more has been said since I had my question formed, but I think it's still relevant. I think it touches on everything that everyone has said, actually. But Andy, you finished with control. I think control versus sort of free exploration as a contrast, and it's come up, I think, in almost everything that you've all said. I think, Tony, you started with the deterministic versus the non-deterministic, and I think that's much less about the technology than about how you see different parts of design, because design is, on one hand, solving a problem, the deterministic, and on the other hand, it's about coming up with new problems, new things that you didn't know that you were solving at the beginning of the process. And in the real world, the world pushes back, right? We have gravity, we have physics, that constrains us, but we also do things in the real world that give us surprise. And so my question, I think, is, the topic that is up there on the screen is physics-informed AI. And I think, Nathan, in the end, you made a great case for why we should bring Newton's equations, very, very strong physical processes into AI. But I can see how that covers the sort of constraint side of things, particularly with something like Newton. I'm not sure. I think, Andy, I can see maybe what you're doing is, the opposite, is the exploration side of things. But how you implement the physics-informed AI is really, really important, because it could do one or the other. And I think I can see the former more than the latter. So I just wonder if you've got specifics as to how we can actually, because it's actually, I think this is more important than just physics, right? If we can get models, AI models, that take in other things, for instance, the laws of grammar are not explicit in a large language model, they're implicit, right? But we could make a much more efficient and a much more accurate model if they were explicit, right? So this is a very, very big problem. So how you actually implement it is important. And I just wonder if you've got solutions or got a roadmap for what you will do to implement it.
Maybe I could just take a first stab at this, but this question is really interesting, especially in regards to world models that people are working on. First of all, the definition of a world model is not very different from different people, but the idea is to sort of create generative spaces. And if you look at what's actually going on in that space, like Jan LeCun has a whole company on this, where essentially the physics constraining is happening in some latent representation that may not be actually humanly interpretable, but that in fact, that's where you put your laws of physics down there, so that whatever happens there, and you then generate it back out to a reality, constraints are held. And in fact, that's a lot of what my group is doing right now, actually, is we are looking to say, I see something that looks very complex. And already, Andy shows this. I can have very simple rules at some scale that produces exceptionally exquisite, multi-scale, interesting features. Imagine if you saw that, you said, you know what, there's a very simple rule that generated this. So, because if you had that, then you would have sort of, in some sense, the right rule for generating that, which is the simplicity down here gives you this. And in fact, part of what we really find in a lot of systems, that's exactly what happens. Down there, it can have something very simple that at scale is like, looks like there's no way you could understand it, but it's actually coming from something simple. So if you can get down to that, and the way I think about that is finding the right coordinates or latent space in which to represent your constraints. And so that's kind of really what our team is doing, is taking these very complex things and finding, can I find a space in which it's very simple to work, and then bring it back out to reality. And that has been fairly effective in many ways, right? And so now you're doing design and you're not having to rely on, I gotta have this massive supercomputer. It's like, actually, once I find the right space to work in, things are actually pretty nicely done there, and then I can come back out. That's at least one perspective. It's not necessarily shared globally, but it's certainly, there's a very big group that kind of believes in that, at least in the physics side of the house.
I mean, I can just provide another perspective, which is just considering the real world data as evidence of behavior, of physical behavior. So when I was doing my doctorate study at UCL, we were all together doing INGs. I did a thing where we had a number of us inside the scanners, like standing in different poses, because my whole thing was all about building, machine models, learned models of human body shape. And this is where I was delving into the notion of dynamic human body shape, where you can create these animations of people walking or doing certain things, but you would simulate, I say in quotes, the movement of their muscles and make it as realistic as possible. So you can either do that through complex physics, and there was some physics at the time, and Maya was the software to use, couldn't afford it. I was a student. So, and it wasn't owned by Autodesk yet, just saying. Anyway, side story. But alternatively, I figured I could take scans of, I had access to 10,000 body scans, surface scans of people, half male, half female, and then I built models of human body shape with those. And, old school, PC analysis, you're kind of, creating this point distribution models, and you reduce variability down to just a number of eigenvectors and eigenvalues, and you can then use those to vary the shape. Taking scans in different poses and building a skeleton model to match the pose of every scan, and building a model of skeleton movement or pose, skeleton pose, pairing that up with surface shape, and together being able to take any person, scan them, put my model to overlay or fit to that person, and then transition them to a new pose without them having ever made that movement, right? But using evidence I'd seen from real-world observation, it looked way more realistic than doing the same animation using a physical-based model. So the notion here is you can reduce some high complexity into this reduction which in my case is eigenvectors and values, and then use traditional keyframing techniques from animation, the animation world, where I have 2 points of known information and I interpolate between them. And this can give you pretty interesting observations that weren't seen but are very close to what you might see in practice. So it's just another perspective on how you might be able to achieve this, again, considering the real world data like scenario and what we can then model with specific like mathematics and statistical approaches.
Thank you.
Yeah, go ahead. Yeah, thanks. Yeah, really good question. So if we think about how design and simulation, all those things are done today, you start with your conceptual design and then you grow to a point where you're quite confident with something and then you want to then do some simulation on it and then you iterate on that. And every time you're iterating, you're adding cost and time and everything else to that. And those simulations are idealizations. They're not they're based on some physics in the world, based on formulas and algorithms and things like that. But they're not considering every kind of physics and every kind of variable, and so we have to add safety factors and things like that to try and make sure we're up here, even though some of the parts are going to be here, some of the parts are going to be here in their performance, and there's a lot of variability and things like that. Then we go through that process, we end up into detailed design. You can't really go back to conceptual design once you're in detailed design. So if you've got a model that's AI and physics informed, you're going to have better simulations. You're going to be able to do a lot more work in that conceptual stage where you are less constrained, and also incorporate those more downstream things that could constrain you, but incorporate them in that very creative process. So yeah, I think it'll change the way we design completely.
Thank you so much. It's really fascinating. And again, just to anchor it a little bit, tie it into design and architecture, structure, weight, how do we actually tackle it, so of course simulating and so on. And just remember that the old way was analysis. So actually designing, analyzing. Oh, I will change it. Okay, so it will work better. Now we generate into a condition, right? So things are kind of basically coming optimized, should come optimized. So that's a game changer. Jazzy?
Hello. I have a maybe slightly long-winded and more philosophical question. We've talked a lot about verifying outputs and focusing on optimization. And I'm curious how this hyper-awareness of constraints shapes the experience, growth, and richness of culture. I mean, I feel like a lot of you have talked about this quite literally in a sense of, like in Barcelona, heat maps and how that will influence structures. But if that didn't influence structures, then how would that influence garments and therefore how we interact? I mean, I feel like this designing to reduce elemental exposure and to reduce error creates this blurry line of where do we draw the line for what is appropriate or ethical use of AI, and to what extent are we simply reactions or outputs of our environments? And this is all to say more so of, do you align more with materialism versus free will? And where do you feel that you align, your industry aligns, and what do you think this means for the direction of the design industry in terms of it being in a AI realm?
And then we will probably wrap it up. So if Pete will have another question, then we'll take it. But otherwise, we'll close.
Okay.
Or maybe Enrico and Rowan. Any questions? Yeah, go ahead.
I hope I'll answer your question. I think that in our industry, I mean, these realms has to work in parallel. They both have to coexist. So because we have in our, let's say, there's a lot of R&D in our office, and that's the beauty of, let's say, my environment. I'm very privileged to actually have all these research around me that can feed back to real projects. And there's a lot of people that actually do a lot of, let's say, experiments and conceptual work that goes to the drawer. I mean, in the sense that we might use it in a different way in another project with another brief, so the knowledge is there, but we're not really actually activating. We're not actually creating a product in that sense. But a lot of our work is actually about human experience. The design is shifting to, it's not really shifting, it's already, but it's performance-led, right? There's a lot of constraints that we need to comply with. And I won't bore you with the details, but yes, you know, for example, you feel here cold or hot, right? So, or the acoustics, the temperature, the comfort levels, the natural daylight provision, all these things have to come into our design. So yes, we have tools to measure it, and we kind of like, run millions of iterations about it. And it might be that then my decision is going to be at the end as simple as, oh, I'm going to add to the design louvers, right? Because it's to export. Oh, I'm going to design this wind catcher that it's going to cool down. So there's millions of ways to actually address one question or one brief. It's never for us one problem to solve. I would say that every project has a lot of problem to solve from a lot of different constraints and a lot of forces that actually impact our work. And we need to somehow mitigate between these worlds. So just to describe a bit our methodologies, like in literally every project, we come up with quite a few options. So we never actually have one distinctive option and we come to client and we say, this is what we think is right. I mean, even when we win a competition, there is a space for actually maneuvering and rethinking about it and trying to explore different avenues. So it's always a conversation between us and the machine and between us and our client. And some clients are more open and they will kind of like drive with us to wherever we want to go. And some actually basically block us I'm saying in a box, but not literally in a box if you've seen our designs. But so it's kind of like ping pong that has to find its ground at the end. But I am super curious to actually find a way to actually use generative tools that will actually allow us to work with structures that we didn't think about, that can actually open up new ways to design, right? Because the structure is so essential. And in many ways, as I showed, it's part of our articulation. It's part of how you experience the space. And by the end of the day, what's important for us is to create a better human experience. That's what we're doing. So I hope I answered.
And just from the tools perspective, well, like why make the AI tools, AI-enabled tools to help with design and the ethics behind all this? I think at the end of the day, so Autodesk will pride itself on being a company that tries to empower our customers to design and make, better things for the world. It could be designed products that are used, that are aesthetically pleasing, entertainment that delivers on the emotional experience. You watch the Avengers or whatever it is, and the way it's rendered and all of the things that you're seeing are quite visually impactful, and therefore quite engaging in that sense. And then if you think about the building, so, Anat's just described how, I'd like to say a customer of ours, and perhaps so still, but as an architect, you're using these design tools to achieve quite compelling, like, human experiences in as far as the buildings that will be inhabited and used by humans. So from a company that makes the tools that enable that to happen, our primary goal is, the problem we're trying to solve is, are we giving the right design freedoms in our tools to allow that kind of creativity to be realized? And when we're failing, then we're not doing our job. And so I think the ethical side of perhaps why build the AI tools is we're just wanting to enhance the creativity that's out there, empowering our users to achieve these amazing things. The AI is just an accelerating tool. It's not there to replace their creativity or impact them in negative ways. The way we're doing it is very much to help them succeed and to get their work done faster, be more productive, be able to achieve more of these delightful outcomes. That's the primary goal. And so I think keeping a sense of what really matters for you as an individual, as a business, is super important, right? Because that's how you get to that end goal together. It's not just about the company making the software, it's the company that makes the software that helps people that use the software achieve the right outcomes. That's I think, the complete story that we want to be thinking about as well.
Thank you very much. Yeah.
I'm just on that point of enabling. I mean, I think that at the moment there are not enough trained data sets in order to actually allow for the way that we want to design. And as you've seen, every project we try another angle. I mean, there's no two alike. I'm not sure when people say that they recognize Zaha. I don't know what they say, because in the years that I work there, I've seen so many very different iterations. So I'm curious if you think that, I mean, this is feasible, because in the, let's say, I'm simplifying, the question in the sense that I'm saying, okay, in an orthogonal world, yes, that could happen. But at the moment, training enough data set that could generate something that we would find compelling, so we could offer it to the world, is this something that you see happening very quickly?
It's something that is definitely being worked on. It's like, how big is your data size? And there is a ballpark figure. People say, do you have 10,000 examples, for example, right? And that's in the world of the neural nets. I mean, if you can go back in time, it's really around the dimensionality of the data you want to train on, and and how many, say, sample points do you need, or the feature vector size is another way to phrase it. What's that feature size, and hence how many samples do you need to have a good representation of your variations in your observed set. And so I can't give you the answer for, say, what is good for your building structures, but it's definitely a consideration that we take into account, because if you look at even how people use, let's take the context of language, large language models, where they fine-tune an existing model with new data to create a specialization there that is then relevant and quite good. Well, that could be an approach that is explored. So it's something that can come from a conversation, perhaps with our teams, to just see like what's possible, for example. Yeah.
We have to wrap it up. That's a really nice ending, actually. I just want to say, Jazzy, one thing for everyone. We are designers, like dancers are dancers. Maybe I mentioned that before, but dancers dance not only to please the audience, they're not only performing, right? They also dance because they like to dance. And we are designers because we like to design as well. So there's always like judgment to apply. It's for us to work with, so that's why the H to M to H thing is like, take it back, apply judgment, hack it, form it, design it, and go back and maybe run it again, okay? And then apply judgment again. So this is for us to play with. I think it's really important to remember, it's our world. I mean, machines can help, but it's also for us to enjoy, making things. And so thank you so much, everyone. Thank you for a dream panel, dream team. Maybe we can run it again in a year or two to update everything, see where we are. Things are running so quickly. Things are running so quickly. So yeah, within half a year, you will see new things coming up. So yeah, thank you so much. Thank you to the YouTube. Thank you to the YouTube stream people that joined all around the world. I didn't really refer to them, but there are some comments and hellos from YouTube. Thank you. Speakers and friends, we're going to the St. Martin's bar for a little drink. If you'd like to join. What do you think? There's rock and roll band. You triggered